Chapter 11. Big Data. Section 1. Big Data and Cursor. We'll talk about how to deal with big data in this chapter. The so-called big data here refers to the data that cannot be loaded in the memory. It is generally stored on the hard disk in the form of file or in the database. This book does not involve the database, but only the big data in the file. Excel files are generally not too large since it has the maximum number of rows. Large files are usually in the text or CSV format mentioned before. According to the memory of modern computers, it takes tens of millions or even hundreds of millions of lines of data to be big, and the file size will be several gigabytes or dozens of gigabytes or more. In fact, we rarely encounter such a large amount of data in our daily desktop work, so the operation methods mentioned before are sufficient in most scenarios. However, as a complete book, we still introduce the processing methods of big data. Is there any difference between big data and the data we processed earlier? Can't the methods we learned earlier be used? The processing methods described in the previous chapters are all for data in memory. The file data used is also processed after being read into memory. Because the CPU can only directly process data in memory, it cannot directly process the hard disk and other non-memory data. Can we do this, give an address for all the data on the hard disk, temporarily read it into the memory from the hard disk when we need to use it, throw it away when it has been used, and write it back to the hard disk if we need to change it, and this way it looks like directly operating a large piece of memory? In theory, it is possible. Indeed, there are programs in some scenarios that do this. For example, Windows has a system cache to do this. But it is hard for structured data operation to do this. Is that because there is any essential difference between memory and hard disk? Yes, in IT terms, memory allows random small piece accessing, that is, the data under an address can be retrieved by randomly giving the address of a piece of memory. For example, when using a sequence, we can access any member with a sequence number. The hard disk can't do that. The hard disk is more suitable for continuous batch accessing. It can only read and write the whole block, at least one minimum unit at a time. The specific size is related to the operating system. At present, most computers are 4096 bytes, and even if only an integer of 4 or 8 bytes is read, it has to read in the whole block. If a large number of small pieces of data at various addresses are read, that is, many places are accessed, and each place has a small piece of data, which is actually a very common situation, then the amount of data read is actually very large, resulting in poor performance. The old mechanical hard disk cannot support high-frequency random access, and the performance degradation is very serious. Because of these troubles, for the scenario of structured data operation, no one simulates the hard disk as memory. Moreover, what's more troublesome is that the operating system does not do any special work for structured data. It only reads and writes file for the data on the hard disk, while operating files is a very complex thing, and this will further reduce the performance. What can we do? We can't directly access the structured data on the hard disk with the previous method. We usually use cursor technology to complete the operation. When we open a data file, the cursor is like a pointer. First it points to the first record of the file, and then several records can be read into memory for processing. During the reading process, the cursor pointer will also move forward. After the data in memory is processed and discarded, the next batch of data will be read from the current position of the cursor for processing. This process is repeated until all the data are read into memory and processed. Because the cursor will read a batch of data every time, it usually occupies multiple blocks of the hard disk, and this is actually batch continuous access, and the difficulty of hard disk is avoided. However, due to the special structure of most data files such as text and CSV, the cursor usually can only move forward, not backward. The cost of moving backward is very high. Even moving forward, it can't jump and can only traverse row by row. In other words, accessing data with a cursor has lost randomness. Therefore, many of the operation methods mentioned before cannot be used. We need to design a set of functions for the cursor. Let's talk about cursor-related functions. In order to do the experiment, we first generate a large file, a simplified order table. The export function will write the table sequence to the file. At A option means to append when writing. Thus, the file will be appended 1,000 times, and less than 10,000 records will be written each time, with a total of less than 10 million records. At T means that the first line of the file writes the field names as the title, which is the same as at T in XLS import function. The ID field can act as the primary key, but the primary key cannot be really established in the file data. DT is the date. The data generated each time is of the same day, and it increases with the loop variable A2, which can ensure that the date is orderly, which will be used later. The time information of now function needs to be discarded. Amount and quantity can be generated randomly. Note that the original data.txt should be deleted before execution, otherwise a batch of data will be added after the current file. In addition, it's better to add the absolute path of the file in actual use, otherwise you may not find where the file is written because the current path is uncertain. Let's first count the total number of records in this file. The cursor function will open the file and create a cursor, which is also a complex object, at T indicating that the first line of the file is the title. The fetch function of the cursor will read out a table sequence composed of a specified number of records and move forward. The next fetch will be the next batch of records. If the end of the file is encountered in the process of reading, all the remaining records will be read, therefore, the desired number of records may not always be read out. When there is nothing to be read at the end of file, null will be returned. If we understand the above knowledge, this code is easy to understand. Do an endless loop, read 10,000 records each time, and jump out of the loop after the reading is finished. In the process, add up the number of records read each time to get the result, which is stored in A1. On this basis, let's calculate the average order amount. The sum can also be calculated in the same loop. To calculate the sum, we only need to read the amount field, and to count the number of records, randomly reading one field is enough. It's not necessary to read all the fields. If we read less, the speed will be faster. We can write the fields to be read in the parameter of the cursor function, so that the table sequence fetched will have only a few fields, and the unnecessary fields do not have to be read in. This is an important difference between external storage calculation and in-memory calculation. We never pay attention to this problem in in-memory calculation. The structure of this endless loop is a fixed pattern. It is a little troublesome to write every time. In addition, it may happen that B3 is forgotten to write or written wrong, which will really become an endless loop. SPL actually supports direct looping against cursor. The for statement can loop through the cursor. The following integer is the number of records read out each cycle, and the loop variable is the table sequence read in. When the data cannot be read out, the loop will naturally stop, so there is no need to write fetch and end conditions, and the code is simpler. The process of using loop to read the data in the cursor in turn to do operation is called traversal of the cursor. Recalling the previous rules, the cursor traversal can only move forward, and can only traverse once. After all the data in the cursor has been read once, the cursor traversal ends, and the cursor is useless and can no longer read data. To read the data from the beginning again, you have to recreate a new cursor. Section 2. Functions on cursor. To only count the number of records, SPL also has a skip function. Skip is intended to skip several records without reading, and return the number of skipped records. When there is no parameter, it will go to the end, and the number of skipped records returned is the total number of records. It seems that it will be easier to directly use the functions on cursor. Are there corresponding cursor functions for operations like sum? After all, it's still troublesome to write a loop by yourself. For example, you need to set an initial value for sum and max. SPL does not have a sum function for cursor, but has groups function. The average order amount in the previous section can be written like this. We learned that when the first parameter of the groups function is filled with blank, it means that the whole data table is divided into one group, which is equivalent to summarizing the whole table, so the order amount and quantity of all the records can be recorded. The result set of A2 is a data table with only one row of record, and the average value is obtained by the calculation of A3. Why not provide a sum and count function for the cursor like for a sequence? Because the cursor traversal is very slow, we should calculate as many results as possible during the traversal. If we provide functions such as sum and count, we need to traverse the cursor once for sum and once again for count. The performance will be very poor. It is also troublesome to create a new cursor in the code, so SPL does not provide it at all. Directly calculate multiple results in one traversal in groups function. However, if we always use groups function to summarize the whole table, it will always return a table sequence with only one row of record. Although there is no problem in use, it still does not feel good. And we also need to get new field names. It is a little troublesome. Therefore, SPL provides a total function, and it can be slightly simplified. The total function also requires one-time traversal to calculate multiple values, but it returns as a sequence without using the field names. Since it is the groups function, it can also be used for group aggregation, right? Yes, for example, we can calculate the total order amount and order quantity of each area. Note that the area field should also be fetched this time. It seems that there is no difference in code between doing group aggregation for cursor and for table sequence or record sequence before. It's true, but the cursor is still special. For example, we want to do another grouping by month. If it's a record sequence, just write another groups. But if it's a cursor, it can't be used again. It has finished traversing and can't get records. At this time, we need to recreate a new cursor and then do groups. But in this way, the cursor data is traversed twice, and the speed is relatively slow. There is indeed this problem. SPL also provides a method to calculate multiple sets of aggregate values in the process of one cursor traversal, which is called traversal reuse. However, these contents belong to the category of performance optimization, which can only be explained clearly by adding new concepts. They are beyond the design outline of this book, so they are not discussed here. You can refer to other documents of SPL if interested. If you use SQL, you can only traverse multiple times. It does not support traversal reuse. There is a groups function for the cursor, but there is no corresponding group function. In fact, SPL also has this function, but the use conditions are limited, and it does not correspond to groups. We'll mention it in the next section. In other words, the groups function of the cursor does not use the group function to divide into subsets first, and then summarize them. Why? Because it is not necessary. Actually, the groups function for the table sequence and record sequence also does not divide into grouping subsets first and then perform summary calculation. There are many summary calculations, such as sum, count, max, which can be implemented by accessing the set members in turn in a loop. Each member can be used only once, and there is no need for the random access we mentioned earlier, so the operation efficiency is higher. If you carefully read the iterative function in Chapter 5, you will understand this principle more thoroughly. Then why doesn't the cursor have a corresponding group function? Cursor is introduced to handle large data that cannot be loaded into memory. If the original data table cannot be loaded into memory, it is obviously impossible to load all grouping subsets. If the group function is provided, it is necessary to keep these grouping subsets in external storage, which has very poor performance and is very troublesome. For the operation that must be realized by grouping subsets, we will think of other better ways to do it, so we do not provide this operation. Now that we understand the aggregation and grouping operations on a cursor, let's move on to other operations. What will the select function look like on a cursor? For example, we want to find orders with an order amount exceeding 5,000. At this time, it is very different from the operation of sequence and record sequence. For the selection function of the record sequence, the result record sequence is calculated directly, and we can view the members. However, it cannot be done for the cursor. Because the cursor corresponds to big data, the selected result may still be big data. We can't calculate it into a table sequence in memory. It has also to be a cursor. Therefore, the select function on the cursor still returns a cursor. Then, how do we view the selected result? We use fetch function. Since the selected cursor is still a cursor, we can also use the fetch function to fetch data. However, because it is a cursor, we can't fetch all the data, and we can only get part of it at a time. A2 conditionally filters the cursor and still returns a cursor. Then A3 can get the table sequence composed of 100 records to examine. When you execute this code, you can look at the return value of A2 and find that it is a strange thing. You can't see the data in the cursor when it is not fetched. It can't be displayed anyway, so SPL just displays it as the name of the internal object. However, what exactly does it mean to execute the select function against the cursor? Will it traverse the data in the cursor once? It should not. Otherwise, where will the qualified records be placed in the traversal process? As we said, it can't be loaded in memory. Shall it be put into the hard disk? SPL does not do this, and there is no need to do so. The select function of the cursor does not actually do any substantive selection action. It just remembers that there is a selection action to be done on the cursor. Only when fetching data will SPL check that there is a select action on the cursor, and only then will it really perform condition judgment to select records. After selecting the records required by fetch, for example, 100 records here, it stops calculating and waits for the next fetch to calculate again. The cursor returned by the select function is called a deferred cursor. It will perform substantive calculation only when the data is really fetched. This is different from the groups function just mentioned. Groups function will immediately trigger the cursor traversal action, and the returned is no longer a cursor. When learning a cursor function, you should know its return value and whether it is a deferred cursor. Deferred cursor technology allows cursor-related code to be written much like calculations of a record sequence. For example, we want to group and summarize orders with an amount of more than 5,000 by area. If it is a record sequence, we know that we just need to execute the select function and then the groups function. The same is true for cursor. It is exactly the same as the operation of a record sequence, and is very simple. Therefore, we can usually not pay much attention to whether the cursors returned by these functions are deferred. It is simply understood that these functions are performing corresponding calculations, and there is generally no problem. However, we still need to know this mechanism, which is necessary when carefully analyzing the running results of some code. However, cursor still has a key difference from record sequence. After we execute select function to a certain record sequence, we will get a new record sequence, but the original record sequence will not change, and we can still continue to do various other calculations. The new cursor obtained after executing select to a cursor is related to the original cursor. In the process of traversing the new cursor, the original cursor will also be traversed at the same time. When the new cursor is traversed and cannot be reused, the original cursor will also be traversed and cannot be reused. Conversely, traversing the original cursor will also affect the new cursor. After a new deferred cursor is obtained by executing a function on a cursor, in principle, the original cursor should not be used again, otherwise there will be very chaotic consequences. Cursor and record sequence are essentially different. After all, there are great differences between memory and external storage. SPL just tried to make them similar, so it will be more convenient to learn and write code. Because the cursor cannot be accessed randomly, positioning is meaningless, so there are no functions like pSelect on the cursor. In addition, align and enum functions are often only related to small data, so there is no corresponding cursor version. But the functions new, run, and derive are very meaningful. These are also deferred cursors. For example, we add an average unit price field to orders with an order amount of more than 5,000. We can create another deferred cursor based on the deferred cursor. SPL will not calculate immediately, but marks down that there is a select action and a derive action on the cursor, which will be executed one by one when fetching. New function and run function are similar. In fact, the news function for expansion can also be executed on cursor. There are no more examples here. Foreign key-related switch and join functions are meaningful to cursor. Assuming that each region will have its own tax rate, now we want to calculate the total number and amount of orders with tax exceeding 100 by month. The switch function also returns a deferred cursor. In the process of groups calculation, only when the data is read in will the switch function be actually processed, that is, converting the foreign key field area into the record of the dimension table. Similarly, we want to add a tax field to the orders with an amount of more than 5,000 and write it to another file. The export function can write the cursor directly to the file. @C means to write it as a comma-separated CSV file, A T means to write the field names as the first line as the title. In A6, we first use the join function to add the tax rate to the cursor data, and then use run to change the tax rate into tax. The functions of deferring cursor can be used at multiple steps, and the writing method is exactly the same as the record sequence in memory. Section 3. Ordered cursor. Let's look at the group function on the cursor. As mentioned earlier, for a cursor, we can't keep all the grouped subsets after grouping in memory to continue calculation, but putting them in external storage will be very troublesome and seriously affect the performance, and the losses often outweigh the gains. However, there is a case where a grouping subset can be placed in memory for processing. If the data in the cursor is in order to the grouping key values, for example, they are always from small to large or from large to small, and each grouping subset is not large, we can always keep a grouping subset in memory. After completing the relevant summary operation for it, the current grouping subset can be discarded, and then read in the next grouping subset, and so on. In this way, we can complete some operations that must rely on grouping subsets without large memory. This is the group function on cursor, which requires that the cursor is ordered to grouping key values. Moreover, this function returns a deferred cursor. When generating data before, we ensured that the data in the cursor is orderly to the DT field. Now look at the result of A3. The fetch result is not a tail sequence, but a sequence with two members. Double-click one of them to see. This looks like a table sequence. It's one group, a record sequence composed of records taken from cursor data. In fact, it is a grouping subset. Different from the sequence, the group function and groups function of the cursor do not correspond. The group function requires that the cursor data is ordered to the grouping key values, and returns a deferred cursor. It does not calculate immediately. Groups function will immediately traverse the cursor for calculation. A cursor with ordered data for a key value is called an ordered cursor. Using this grouping subset, let's calculate the order amount and number of orders in the region with the largest order amount every day. This requires to do another group aggregation to the grouping subset and get the record where the maximum value is located. Using the code we've learned before, it's easy. It can be seen that functions such as a dot parentheses can also be used for cursor, and it is also a deferred cursor. Moreover, in the next round of calculation based on deferred cursor, tilde can be used to represent the current member like in a loop function, but it can't use hash or square brackets. Because the relative position information of the cursor is complex, SPL has not implemented it yet, the subsequent data has not been read out, and forward adjacent reference can't be implemented. maxp at A will return a sequence, which is actually a record sequence here, so A3 will actually be a cursor equivalent to a two-layer sequence. It takes another conjunction to become a single-layer sequence. Conjunction function also returns a deferred cursor. It also needs the fetch function to get the result. The fetch function without parameter will fetch all the data. We know that the data has only 1000 days, the final result set will not be very large and can be fetched completely. Moreover, from the group function itself and here, we can also see that cursor does not always read out a table sequence. It may fetch out a two-layer sequence. In fact, the cursor corresponds to a sequence, not always a table sequence. The result of the fetch function is also a subsequence, and its member may be any data that can be member of a sequence. The group function also has the @I option, and same as the group @I of a record sequence, it is interpreted as dividing into a new group when the condition is true, and it also returns a deferred cursor. In addition, the group function of the cursor that uses semicolon between parameters will also be interpreted as group.new like an in-memory record sequence, and will also return a deferred cursor. Groups also has the @O and @I options, which can perform ordered grouping to improve running performance, but groups always calculate immediately, and will traverse immediately even for ordered cursor. The result of this code is the same as that without @O, but with @O, the performance is better when using order. Similar to the previous discussion on ordered grouping, ordered cursor can also be used to assist in log parsing. Usually, the log is really large and cannot be read into memory, so it is more necessary to use ordered cursor. SPL also extends the for statement to directly support fetching one grouping subset from an ordered cursor at a time. Similar to the case of small data, we also discuss it in three cases. 1. Each n line corresponds to an event. Note that when reading text with a cursor, add the @si option to the cursor function, so that it will read out a sequence composed of strings. If there is no option, it will try to interpret it as a table sequence, but the log data is often messy, and it is likely to make errors when directly parsing it as a table sequence. 2. The number of lines is not fixed. There will be a fixed starting string before each event. To add parameter 1, it means that one grouping subset is read out at a time, or directly use the extended for statement. Note that it is a semicolon between the cursor and the following condition. 3. The number of lines is not fixed. Each line of the same event has the same prefix, such as the user ID of the log. Read in one grouping subset at a time, or use the extended for statement. You can refer to the previous code that uses ordered grouping to process small data. Section 4. Big cursor. We haven't learned the sorting of big data yet. Sorting operation is very different. Its calculation result is as large as the source data. If the source data cannot be loaded in memory, the result cannot be loaded for sure, but unlike select and new functions, it cannot be calculated while traversing. The sorting of big data can only be solved by using external storage as buffer. The general steps are as follows: read in some data, sort in memory and write out the result, then read the next part, sort and write, and so on. Finally, a batch of ordered intermediate results will be obtained, and then the merging algorithm will be used to concatenate these intermediate results. This process is complex and beyond the design scope of this book, and we won't talk about the detailed principle here. SPL provides the sortX function to perform big data sorting. This function implements all the above series of processes. Because the sorting result is still big data, sortX will also return a cursor, but it is not a deferred cursor. SortX will calculate immediately, and the returned cursor is based on the intermediate results described above. For example, we want to arrange the order data according to the average unit price from large to small, and then write it to another file. Because sorting is from large to small, sortX uses negative number as the parameter. A2 is a cursor after calculation, which cannot be viewed directly. You can get data with fetch function or write to another file like A3. SortX calculates immediately. When it returns after execution, cursor A1 has been traversed. At this time, even deleting data.txt will not affect the action of A3. This is completely different from functions like select. The deferred cursor returned by the select function will be traversed synchronously with its basis cursor in the future. As a reminder, sortX may be slow and need to wait for some time after running. It also takes up some hard disk space used to store intermediate results. sproc will use the operating system temporary directory by default, or you can set the temporary directory yourself in the options. In fact, sorting for big data itself is not commonly used. We usually don't care about the full sorting result of big data, but only the top n. However, sorting is often the basis of other big data operations. Without an orderly result, other operations are difficult to do. For example, big grouping. For the groups function we used before, the returned result is a table sequence, that is, small data. However, there is still some kind of group aggregation operation, and its return result will be so huge that the memory can't fit. At this time, there is no way to use groups function, which will lead to memory overflow. However, as we said earlier, if the data is in order to the grouping key values, we can use the method of group function to summarize at the same time during the traversal process, and there will be no overflow. No matter how large the returned grouping result is, it can be calculated normally. For example, we want to do a grouping by two fields amount and quantity to see how many orders there are in each group with different amount and quantity. The grouping result may be 1 million lines, it's not big, but we just regard it as big. Suppose it can't be done with groups. The current data has no order for the combination of these two fields. After sorting, we can use the group function. In this way, we can calculate out the big grouping, but because the result is large, we can only fetch a part to view or write to another file. We can do other calculations based on it. For example, we want to calculate the total amount and quantity for groups with more than 5 orders of the same amount and quantity. The group function returns a deferred cursor. We can attach another select operation, and then traverse it with total function. Because big grouping is commonly used, SPL provides a groupX function which does sorting and grouping together. The above code can be simplified like this. Parameter rules of groupX are the same as those of groups, but it assumes that the returned result set is large, so it will sort first, then do an ordered grouping, and finally return a cursor. Like sortX function, this is not a deferred cursor. When the two actions are executed together, not only the syntax is simpler, but also the execution speed is better. However, like sortX, it will temporarily occupy hard disk space. In addition to the big grouping, there is also the big merging calculation. Similar to the previous example of merging calculation, if we have two large order files on hand, we need to merge them, and the data must be orderly in advance. Assuming that the data is ordered by ID, we can directly use mergeX function to calculate union. The parameters here are the same as those of merge function, but generally we will not establish a primary key on the cursor, so we need to write the association key used in the merge operation. Because the result set may be large, mergeX also returns a cursor, but it is a deferred cursor and will not traverse automatically. Unlike select function, mergeX may generate a deferred cursor for multiple basis cursors. After traversing it, it will also traverse all the basis cursors. The previously mentioned select and other functions only have one basis cursor. The T function uses the @C option to generate a cursor, and it will automatically select the opening method according to the file extension. It can also be used to write out. @C means to write out the cursor, and the write-out method will also be selected according to the file extension. Unlike the in-memory merge function, mergeX function requires that the cursor data must be in order to work, and there is no @O option. After sorting, the operation that can only be realized by random access can be changed into sequential access. Another similar case is the join operation. Finding associated records with associated key values originally requires random access, but if the data is in order with associated key, sequential access can achieve the goal. SPL also provides a joinX function with X to solve the big join. The joinX function can support the homo-dimensional association and primary subassociation. It also returns a deferred cursor. The form of the table sequence fetched from it is similar to that of the join function in memory. The value of each field is the record in each associated cursor, and then you can continue to use the new function to realize further reference calculation. Similarly, joinX function supports left join and full join with @1 and @F. We won't give detailed examples here. You can generate two data tables with different structures to try to do a big join, and you need to ensure that the association key is orderly, or you should sort with sortX function first. You may find that there is another situation we have not mentioned, that is, in the case of foreign key association, the dimension table is too large to be loaded into memory. When we talked about switch and join functions related to foreign key on the cursor, the fact table data comes from the cursor, but the dimension table is still a table sequence in memory. In this case, at present, foreign key can only be understood as join operation and then implemented by joinX function. If the data is disordered to the foreign key of the fact table and the primary key of the dimension table in advance, it needs to be sorted first. Moreover, each joinX function can only resolve one foreign key association, and multiple foreign keys have to do joinX multiple times. While the switch and join for the in-memory dimension table can resolve multiple foreign keys in one traversal. Unlike select, groupX and other functions that only work for one cursor, mergeX and joinX work for multiple cursors. So, is it possible to merge and join big data and small data together? It does exist. The merging and join operations of big data and small data are also big data, and the method of big data should be used. In this case, the small data in memory, that is, the table sequence, should be converted into a cursor, and then the cursor method should be used for operation. SPL provides cursor function to convert the table sequence or record sequence into a cursor, so that small in-memory data can be simulated into large data and operated together with a file cursor. There are no more examples here. You can refer to relevant help documents when you need them. We have now learned to use cursor to implement big data operations, but we can only do it right. Another important goal of big data computing is to do it fast, which is also a very complex task, or even a more complex task. Like the traversal reuse technology mentioned earlier, these contents are far beyond the design scope of this book. Here, we just give you an impression. The content of how to improve the performance of big data operation is enough to write another book of the same length. Many calculation methods need to be redesigned, especially to find ways to avoid substantive sorting, because sorting is a very slow action. In the conventional programming languages for structured data processing, SQL can deal with big data. SQL even achieves data size transparency, that is, users do not need to care about the size of data, which obviously saves people a lot of troubles. This is a huge advantage of SQL. However, using SQL usually needs to load the data into the database, which is too complex and beyond the ability of most non-professional programmers. SPROC provides the function of using basic SQL for files and can support most big data operations, so as to avoid the trouble of loading data into the database. Python is also often used for structured data calculation, but it has no cursor object, and it is very troublesome when processing big data. It is equivalent to implementing the cursor action by yourself, which is basically an impossible task for non-professionals.